these things usually start out where we prime the pump and then questions come later. How many, well, there's a lot of lunches in here that don't have people sitting behind them. Snooze, you lose, huh? All right. Oh, what are we at on the time? Okay, 45 minutes. Thank you. Give me like a 140 or something. Okay. DDD. Oh, there's a great question. Okay, this is pretty good. All right. I'm going to start there. I have some basic questions that'll really make a stepping stone into the rest of the other questions that we have. One of them says, what spectrograph for what science? The other one says, what spectrograph for what telescope? Huh? Pretty much, yeah. The beautiful thing about spectroscopy is you just make a rainbow. And if you get it in focus, you get astrophysical information. The more focus you get, the more information you get. The problem comes down to, as with the dispersion axis, is the light is starting to be spread out. To get good resolution, you got to wipe it really, 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 really thin so that you're zoomed in. So if you think about it in photometric terms, it's like focus. If your star is way out of focus, you're going to have to run a lot longer exposure, but you get, more area is covered. So in general, for run-of-the-mill stellar classification of, let's say, what do we want to pick on? A G star, since we live with one, and it's right out of your window. And for our friends from northern climes, that's all you will probably see, except for Polaris, apparently, for about the next 6 weeks. So what goes on is the light comes in through the telescope and gets focused into a star image. First problem, what's the focal length of the telescope? The longer the focal length of the telescope, the bigger the star size image. Now let's go all the way through the spectrograph to the sensor. Essentially, the information on the sensor is the superposition of a lot of information that's come through the entire system. It includes making a very bad image of the slit, and the width of that slit directly affects resolution. So now we've got long focal length, we need a wide slit, short focal length like a C8 or a C9.5, or means that you can have a narrow slit. If you live in Miami with very calm air, you get smaller stars, you get a smaller slit.
There's something even more important here, Wayne, with the fast F ratio versus the slow F ratio. With the very small F ratio, and John Menke has alluded to this already, the problem is that the beam size is changing very quickly. It's in focus at the slit, but when it goes through the slit on the other side, it's diverging again. And you need to have your spectrograph work at the best efficiency. You need your collimator to fill the beam.
Let me get there.
But that's probably the most important thing here. No. Not the amount of light you're letting through the slit, but how that beam is diverging on the other side.
Okay.
And that's why long focus instruments. That's why long focus instruments are favored, right? Because the beam doesn't diverge as quickly. You don't need to build a gigantic collimator. You don't need a grating that is 5 feet across for your beam.
I was getting to that point. Okay. It's still a function of focal length. The spot size forms the width of the image of the slit, and the width of that slit is then changed by the ratio of the collimating lens to the camera lens to get good resolution at the sensor. That's the basic way to think about a spectrograph. Now, for those of you who have astrographs with F3 instruments, what Dr. Martin was alluding to is the fact that the beam comes in at a fairly strong angle. You can deal with that strong angle with other optics inside of the spectrograph. For the most part, spectroscopy is done with a F6 or 7 beam, and it's done in such a way that the length of the focal length of the instrument has to go up so that it grabs most, if not all, of the light that came through the slit. What we discovered is that light is all over the place because it quits being an optical beam when it hits the slit, and it turns into a Fourier space, okay? And we've demonstrated that in space with our spectrograph. The next real issue that we get is you're going to lose some light, and no matter what you do, it's how much, what can you have, what can you afford? If I'm building a spectrograph for, say, Embrace, I have the ability to go buy a 6-inch highly machined or highly developed collimating lens, you know, perfect glass for prisms, a shell gratings that are the size of dinner serving trays, things along those lines. But at the end of the day, what we can afford, what we can use, and what matches up to the equipment that we have comes down to, it really makes an important difference on the main focal length of the instrument versus the focal length of the collimating lens. Right now, there are spectrographs on the market, and Jim Grubb's waving a piece of one around right now. Okay, that's the chassis for the Flex Spec one that we developed. That's roughly a Lisa in a different box, the Shellyak Lisa. It's the Lisa was the low spec and low spec 2 were modeled on the Lisa. And the focal length of the collimating lens is somewhere in the 100 to 125 millimeter range. Okay. The collimating lens, what's the collimating lens in a Lisa? 50? Something. 35, 50? Like not collimating, camera lens or objective lens. I'm going for the ratio, okay? I just don't remember what the lens focal length is. 83, okay, that's about a 1/3 to 2/3 ratio. If you go, okay, so one other thing, it says, talking about spectrographs, there's another design of a spectrograph, and that's called a litro design. And that's where the focal length of the collimating lens is the focal length of the camera lens. Often they use the same lens. And that gives you a 1-to-1 ratio. And that means that you need a much longer focal length on the litro in order to survive coming back and having some resolution left at the sensor. That's basically what that comes down to. Some guy who went off and bought himself a 24-inch plane wave and located it far away has got that longer focal length. We're beginning to see longer and longer focal lengths. We're beginning to see longer and longer focal lengths in our community because we're moving away from small telescopes and what we think of as a small telescope, something like an 8-inch Celestron or a f6.7 CDK14. We see a couple 16 inches are in the audience. I've got one, got two. Stan back there's got a 24-inch CDK. I think 20-inch CDK. So you're in good shape. We're seeing more and longer instruments, but these tiny small spectrographs, which are manufactured for the amateur tiny telescope market, won't cut it on these larger telescopes. You can get information out of them, but you're going to lose a lot of light. You're going to lose it at the slit. Yeah. You're going to lose it somewhat inside the instrument.
And let me point out, it's the focal ratio of the collimator that's important. It needs to be matched.
John, let me talk. I don't. You're jumping the needle far ahead of where I'm trying to go. The question here is what spectrograph for what science? Okay, that's a pretty basic question. All right, it comes down, like John was saying, is that if the magnification of the image of the slit is essentially 1 as it comes off the collimator. And as you take a fraction of that, you're concentrating it. So that means you're shrinking the size of the image of that slit narrower and narrower as that ratio grows. We're using a 125 millimeter focal length lens and a 50 millimeter camera lens because we discovered, rather like Tony said in his earlier talk, instead of paying, what was it, $150 or something for an expensive achromat, we paid $50 off of eBay for a camera lens. We sacrificed a little bit of light going through the camera lens, but what we bought for that was the back end of camera lens have this thing basically called a tessar unit in it that flattens it. So we get rid of that bending astigmatism. Tony was able to do a linear fit of the dispersion axis and get excellent science. I can go on like this for hours, but the bottom line comes down to take a look at the focal length of your instrument and make sure, and I'm talking in generic terms here. I'm not talking about exotic instruments like astrographs or things along those lines. You take the focal length of your instrument and you come up with the size of the star on your slit. And since Bob's writing numbers down and he's not a math guy, it's interesting. Okay, if you take this magic formula, which is 206,264.8, so number of arc seconds in a radian, you divide that by the focal length of your telescope, and this is going to sound stupid, but it works, in microns. Okay, just multiply the millimeters by 1,000. And what you wind up with is X arc seconds over here for 1 micron. And then you can plug in how big is that, you know, essentially what's going on there for you. Or you can get essentially, about this for a second. You can do it the other way around. You can say 1 arc second is worth this many microns. And that becomes like a magic number for your telescope. It applies in photometry. How many pixels are you going to cover? Because the slit's right there at the focal plane. Or it comes back and says, how wide of a slit do I need to let that full airy disk, well, of course it goes to infinity on either side, but to get, you know, the arc seeing size of your star through that slit. Now you're getting all of the light through. Now let's talk about 2 problems. There's another problem here. What's parallactic angle? The problem with this is if the slit is too small, the atmosphere is a prism and it makes a little red end and blue end of the star. And if that's not oriented correctly on the slit, as tracking errors go, it usually cheats to the red and underrepresents the blue. If you rotate the slit from a horizontal to a vertical direction, you'll see a change in the shape of your spectrum. That was an easy experiment that we did 2018, I think it was. I'm trying to look around to see. I sent that paper to 2 people at this proceeding. I just don't see who see them here. Anyway, it comes down to if the slit is too narrow, you'll lose part of the spectrum because of parallactic angle. If you're at the zenith, you won't. The lower in air mass you go, the worse it gets. And in different parts of the sky, it's different. Because of, as long as your slit is essentially vertical with a line of altitude and an alt-as type means, the light will come through the slit. The blue part will be at the top of the slit. The red part will be at the bottom of the slit, and that'll come through. If the slit's rotated wrong, you're going to cheat the red or the blue end, and that does make a big difference. In flex spec, we have something called the IMU, the inertial unit, and what that does is that tells us the orientation of the spectrograph, so that we know how to rotate it at any position in the sky, such that the slit is vertical with respect to the line from the zenith down to the horizon, line of altitude, and that makes a bit of a difference. There's really, the answer is what spectrograph for what science? That's mostly a function of how dim of a target do you want to see. If you want to do novae classification with a small telescope, and assuming that the magnitude of the nova is somewhere in the 15, 16, 17 area, R1000 spectrograph, you're not going to be able to get enough light to make a determination. And R600 Alpi starts to push it. If you've got like a C11, maybe a C14, you'll do a little bit better. C14s have a really long focal length, by the way, which gets us into trouble with that spot size thing again. And if you use something like a star analyzer that you can just put in your filter wheel, you can get about an R100 image. In order to classify a supernova, you need a resolution of 10. So this, and that's from, what's her name? Maria Mojaz at Sunnybrook, who runs the database for supernovae. I asked her point blank, what do we need? She said 10. You can do that with photometric filters. Alpi is a good choice there. So Bob, on your Alpi, do you have the slit that has the photometric slit built in with it? Yes. Okay.
I do not have the photometric slit, but sometimes I regret the lack of it.
Right. On FlexSpec, we can dial around. We have a 700 or 700 micron slit we can put on there. You can take color pictures of birds with that thing. Okay. So you would dial it down so that you get, and when you, okay, the bigger the slit, the more light. The other problem you're going to get is the internal focal length of this is also going to magnify the width of your dispersion. It's going to spread it over more pixels. Hold on just a second. I mean, finish my thought here. The star analyzer bolted into your filter wheel has a very short distance that it goes across. It makes a very small image on your sensor. It compresses the spectral range down, which you don't care about at R10. So then you can go after those dimmer supernovae. Jim.
My question was, while we're on the topic of the photometric slit, can you describe I know it's a narrow and a wide slit, but what is the process that you do when you use the photometric slit?
Point and shoot.
As Wayne's described, all other things being equal,
Bob?
higher spectral resolution requires a narrower slit. But that narrow slit's not collecting the entire point spread function. It's subject to all these atmospheric effects, et cetera. So one of the things is if you want to get a spectrum whose integrated energy across all wavelengths represents the totality of the light from the star, sort of like you would get from a photometric measurement, use a really wide slit. It gives you really low resolution, but 100% of the star energy is in there. And you remember all the troubles we've had doing atmospheric response correction. Some of that is slit function because the slit we're using is smaller than the star image. Big photometric slit solves that problem because 100% of the light's going through the photometric slit. And you can even have a little tracking error or parallactic angle dispersion and you still get. Okay, now Tony's going to correct me.
No, not the slightest. I think I've just been reminded that the size you're seeing plays a big part in this, because there's James Lay down in Miami, Florida. He's using an Alpi with a 10 micron slit and getting a resolution of 1,000 on an Alpi, but you don't. Stan's putting a machine down in Chile with sub-arc second seeing. So even though he's got a really long length, smaller, it fits inside a 30 micron slit. Yes, yeah, absolutely.
So the message there is, in addition to negotiating for the cost of the larger telescope, you also need to negotiate the idea of moving to La Serena.
So if I iterate back over the problem again, that's what I was intending to do, is iterate this a little bit. In my backyard, I get 3 or 4 arc seconds of seeing if I don't have a wave cloud. Out at Strasbourg, I get an arc second and a quarter. Jim Lay enjoys half an arc second. Valley up on top of Ball Mountain in Colorado, he gets half an arc second. Tony, what do you usually run? About 2 to 4? 2 to 4 arc seconds? Yeah, that's about pretty common. Yeah. So that goes back to if you calculate what the point, what the pixel size of your star is at your focal plane, you accommodate that with the slit width. The next thing is in F ratio and so forth notwithstanding, are you fully illuminating your collimator? Then the size of the collimating lens drives the size of the grating. And then the grating basically says how much dispersion you're going to get. If you're using a 300 line per millimeter, 600 line per millimeter, such, that goes off in the direction of the camera lens. Then the camera lens takes that image and converts it back down into essentially a virtual image at the sensor. So the ratio of the collimator lens to that camera lens, and often it's called, I think it's called the objective lens in the Shellyak world. Europeans, I guess, use different vocabulary than Schroeder did anyway. The result is in a litro, it's 1-to-1. So that basically means you've got to have a really long instrument to make that work. And they fold it around and do stuff in the LiRes 3. The Alpi is a different model altogether. It uses a combination of a grating and a prism to achieve its results, and it gets a pretty decent dispersion over a short distance. And that models a different kind of spectrograph called a Tragos, which I think there are numerous designs of those all over the place. So when it comes down to what spectrograph for what science, it comes down to the amount of energy that you're getting that describes the science that you want to see. If you're doing BE fast rotating stars, you're primarily looking at the hydrogen alpha line, and that's a pretty big line. And so you're getting a lot of decent energy there. You can look at a BE star that's close by, and in relatively reasonable exposure times, you can do things. If you take that same star and move it halfway across the galaxy, the distance modulus is going to drop your light to nothing. You really can't really observe those. So part and parcel of the question of what spectrograph for what science is something I've been kind of developing the idea of. It's called the flux radius that you have with your instrumentation package. And that just comes down to aperture, how much of an area of light that you can actually accept. And you're going to concentrate that down to a point where you'll get enough ADUs on your sensor to describe the science that you want to have. Really, is no real simple question to this. And I think FlexSpec team wrestled with this a little bit. It's like having, with photometry, you've got basically one knob, and that's the filter. And you put the light through there and you calculate the ADUs that you're going to get, the attenuation from your filter, and you're done. In a spectrograph, you've got a whole series of knobs that you can turn based on the geometry of your design, whether it's a classical, a Chernzy-Turner, which I think is the UVEX, or if it's a litro type design, or if it's in a shell. That's a problem that you get into. Okay. There's one other thing I want to go into. If gratings come with something called a grating function, and you can get them that are blazed for blue, green, or red, or other things. And those are about the ones that we can work with. Remember, we work with a wavelength range. I use 3,300 angstroms, up to about 9,000 angstroms. That's my walking around mine. 33 is a little thin, and often I'll go down to 32 for a little bit different reason. 33 is awfully blue. The chips aren't sensitive in blue. You can see these spectra coming along. They should be blazingly bright down here in the UV, but our sensors just don't detect them. The curve will come up, it goes down in the red, and we're done. So if you looked at the quantum efficiency curve, which is another knob that you get, we borrow that one from photometry as well, then that becomes part of the equation on top of it all. Big question is, what science do we want to do to begin with? I think there's some people in the room that are looking at red dwarf stars. Is that right?
Whoever wrote the question, are you willing to elaborate a little on what you would like to be doing?
ISM, but I don't have enough flux. Oh, there is one other thing. Hold on. We had a request from one of the paper authors to yesterday, Stephen Hill. Stephen Hill wants to look at atmosphere of planets, and these puppies are nearby and bright. What about first magnitude to about -2 for Jupiter, -4 for Venus? And now I think I will let the blood return to his
I
hands.
can speak to that because actually we do that with the 10C spectrograph at our observatory.
Yeah.
So you need, and to do like methane bands in the outer planets, which is why I was really interested in his talk really too. To do that, you need a spectral resolution of a few thousand. A little more would be better, but a few thousand gives you kind of like a broad look at the bands. And of course, I'm using a 20-inch telescope. That's an f/13, which is optimized for that type of work. But you ought to be able to do it if you have a spectral resolution of about 1,000, and you want to find the spectral region where you got the bands. And we can talk about slit width later, but I just want to interject that when you change the slit width on the Space Telescope Imaging Spectrograph, you don't change the resolution. And it's the same for all the other spectrographs here too.
Okay. Greg?
Hello? Hello? There you go. One's a comment, and that is about the F ratio of the scope, since that came up earlier. One of the big issues is finding the camera lens when you start getting, so as you come off the grating, you have whatever your F ratio is basically, or the size of your collimated beam, but now with dispersion it's getting wider. And if you start looking for commercial camera lenses, you'll find out very quickly that beyond about 40 millimeters or 50 millimeters in diameter, they get very scarce and or very expensive. And so there's some physical aspects of this as far as availability you have to be careful with. It particularly talks to really fast systems. It gets really difficult to design a system below about F4. You can do it, but you're talking custom optics pretty fast. The other question was on the BE stars and stuff. From the talks, I get the impression there's two issues. One is you want to go faint just to see the flares. And I'm wondering if you need much R value there. Could you go with a prism, for instance, and go fainter? And then if you're looking for Doppler shifts, you need higher resolution. So there may be a case for two spectrographs for two different parts of that science.
Okay, Greg brings up an interesting point. There's something you guys, okay, you got to have some math. Sorry, we're in spectroscopy. It's pretty easy stuff. It's basically delta lambda over lambda is delta nu over nu is equal to C over V. And what that's telling you is in terms of resolution, what do you get, right? So if I take a lambda of 6,000, we'll call that hydrogen alpha to keep the math easy for Bob and me, because I'm up here having to think it. And I do a delta lambda over that I'm looking for. I'm basically looking for an R factor of 100. So that basically means that delta lambda over lambda means I need 65. Okay, and so that means I'm going to have a fairly broad width in there. If I go up to like an R of 1,000, that drops down to 6. So now I'm getting about 6 angstroms per theoretical resolution unit. Bearing in mind, I'm going to drive this through and it's going to go to heck through for a whole bunch of other reasons. if I really work it out, it turns out to be, what is it, John? What's your working around number? About 70 kilometers per angstrom for velocity in velocity space. Delta V over C. Delta lambda over lambda is equal to V over C. So if I've got 1 angstrom of resolution, what's my velocity?
62.
62. Yeah. I walk around with 70.
What
in my
units are that
pocket.
in?
Kilometers per second.
Kilometers per second.
Kilometers per second. That's 62 kilometers a second. So if my physics is smaller than that, I need more resolution. What was SS, what was it, 443?
Oh, yeah, the jet velocity is a quarter of the speed of light.
Yeah, okay. So
Delta
what they're
V is-
looking
so
at is
Delta
they're
lambda
looking,
is big.
they're looking at a mass that's being ejected and spun up by field coming off of this thing that's moving at what, 0.26 the speed of light, wasn't it? If I remember the number correctly. So the fellow that brought that to our really pointed attention, Dr. Steve Shore, we asked him point blank, what resolution do you want? And he says he wants R5000 to do his science. His science is cataclysmic novae and classical novae. We also asked him, by the way, what signal to noise ratio do you want? Because that's when we start losing light, we start messing that number up. He said 20 to 25 would be good for him. Whereas in photometry, 1% photometry is an SNR of about 100 to 1. Okay, so that means it can be 4 or 5 times worse and still be able to get to the science that I need to get to.
Let me interject that this is a sampling issue as well, because you don't want to be right at the minimum velocity resolution you want. You want to be below that so that you have several, right? So if you want to measure 100 kilometers per second, you're probably better getting at least 3 resolution units in there to measure that 100 kilometers per second. Just simple sampling theory there is a guide I throw in.
Shut off here. Anyway, the next trick is, like John said, that there's that aspect of it. Dr. Guzik wants to look at P and G mode oscillations. I think G mode's the up and down one, right? Yeah. Yeah, so it's okay. What kind of velocities are we looking at? Pretty small. What does that mean?
These are smaller stars, so they're pretty small. Although if Joyce is in and she knows, she can put it in the chat, I'll let you know.
So the real trick comes down to, now I need more and more and more resolution. What does that mean? I need to have more and more and more flux to, when I spread it out at that high resolution across that dispersion axis, I can still make the, I get enough ADU to have the signal to noise ratio that I need. John.
She says centimeter per second, but I don't think she means centimeter per second.
I do.
Did you mean kilometer per second, Joyce?
No.
Here, why don't I try to give Joyce the floor if she could.
I was talking to Tim Brown about this. It's in the centimeter per second range. That's what rave and
centimeters?
Centimeter per second.
Oh, good God. You guys are never going to get, most professionals won't do that.
Okay, I've worked at those velocities before in a spectrograph about twice the size of this room.
Yeah.
Not quite as long, but twice the volume of this room, let's put it that way.
Yeah.
Okay.
Yeah.
And you know what my magnitude limit was? You know what my magnitude? You and snow, right? Okay, well, what I was using was Tel 7 at Kitt Peak. You know what my magnitude limit was? 6. Good luck with that.
Well, we were
Joyce is going, that's almost bright enough.
No?
Some of the stars I would like to observe are magnitude 6 or brighter. And that centimeter per second is for more solar-like oscillations and some of the lower amplitude modes. Possibly some of these higher amplitude modes are meters per second.
Still off by a factor of 3 in our thinking.
No, not a factor of 3. So measuring actual velocities of the modes may be really hard, but maybe you can measure whether there's a close binary companion by radial velocities. If you see two sets of spectral lines, for example, that are going in opposite directions, that would be useful. Or let's see, what else could you do? Just looking at line profile variation, just looking at how a line may change shape with time over the course of a G-mode pulsation, that would be
That's right.
useful. Or
So
looking
that's
at
the
a
width
color,
of a line base versus its amplitude.
right, right. Or looking at a color change in the star during a cycle that might tell you whether that's a spot or a pulsation. So there are some things you could do without measuring centimeter per second radial velocities.
Yeah, I think the divorce would do two things. One, it was to give me permission to have more aperture, but it would be take away all the money to get the aperture. So we joke about that in spousal units. Yes, Mark.
Yeah, so here's an idea I've had for a little while. Trying to get the balance between brightness and resolution needed. How about bright blue stars that are young stars still emerging from a stellar nursery and using their strong light to light up organic compounds in the dust in that nursery? So you've got like a backlit projector, and I wonder if we could actually detect those organic molecules with our scalar devices.
Nope. And the problem is
that. Oh, that's right, because the molecules are infrared.
that's an excellent question, by the way. It's one of my favorite. Okay. And look up the Visos project, Bo Reipert and company. And they're talking about monitoring these things, the pretty picture crowd. Guess where these stellar nurseries are? In awful artful environments. Okay. So we've got a lot of data there we aren't mining correctly. But the real problem is when a star turns on, chances are it turns on inside of a cloud. You've got a lot of dust attenuation in there. And then for molecules, those transitions are in the Passion band or the bracket band. And those are just ones that we can't get at without having a really expensive infrared detector and having all of our optics set up to deal with infrared. Those are molecular transitions. However, our poor little dwarf star guys, they're stuck with molecules in their photosphere that we do see. We do see molecular bands in those areas. Okay. Hopefully that says something. The other thing too, you mentioned really bright young stellar objects. Those are often putting out pretty hard UV. And so a lot of the science there is done with STIS because you have to be on orbit to get at those wavelengths with the Space Telescope Imaging Spectrograph, or with COS, the Cosmic Origin Spectrograph. So no, I really appreciate the question because it really drives home the fact that we live in the Balmer bands. That's it. Most of our physics that we can play with are in Balmer bands. And it's either Balmer band directly, or we can see other physics affecting those wavelengths, and we can observe those wavelengths and infer from the changes that we see there what the other physics is doing. I think Dr. Boyd over here was looking at a UV, what's it called? Raman bands, where you have what do they call it? A fluorescing effect. Raman bands, yeah. Like Raman, yeah. Well, that's noodles, isn't it? Hey, I read the words, So the result is we've got UV activity that gets essentially line doubled and reflected as a broad hump up in the Balmer region that has nothing to do with Balmer physics. Okay. Okay, go for it. Yes, go for it.
Oh, Nick, you're unmuted, or unmute yourself and go right ahead.
I didn't request any question. Thank you.
Okay.
Okay, thank you.
Got one anyway? Okay.
You've got 1 minute and 12 seconds.
How much time do I have left? 1 minute and 12
1
seconds?
minute. We
Okay.
must end in 1 minute. No.
Okay, here's,
In 1 minute, it will be 1:45.
All right.
So,
got-
so that's
I
Mark's
got a question
question.
about fiber optic feeds.
Talk to us at the break because we have a fiber
Okay.
optic expert in the
5 minute
crowd.
warning. My mistake. This is your 5 minute warning.
Okay, so now we have this handwriting that I'm going to have to put my glasses on. But since he's sitting in the audience. What is the educational or science fair activities? Is that what you're saying?
Oh, is that my question?
That's one of them.
Okay, this is a question for the group. Look at the back cover of your proceedings. That's a slitless spectrograph image of a star field. Relatively easy to make. What science or educational projects can be used or can make use of that image? Or ones like it that the kids take for themselves?
Okay. All right. So, so other of Bob's questions are, I'm going to take the
Is that
first
the whole
one.
answer?
Hmm?
I'm going to have to take notes for Rachel. So stellar classification. That's a good answer.
Okay.
Anything else?
Asteroids, fast moving objects, supernova. You could do surveys. You could pick up fainter objects such as Markarian galaxy, various galaxies which are Cepheids.
Planetary nebulae.
Well, there's planetary nebulae, there's Wolf-Rayet
Yeah.
stars like NGC 6666. There's the bubble nebula like NGC,
Yep.
whatever it is, Wolf-Rayet.
stars.
But
Yeah,
you
like
can,
NGC 6668, is it?
yeah,
6666?
you can
Okay.
start.
There's Shellyak, the actual star, not the company that makes the spectrographs.
Algol.
Algol, well, Algol's kind of there, but
You could,
there's a couple of galaxies that you can see rotation curves in, planets you can see
Yes.
rotation curves in.
yes, it can.
Huh?
Actually,
Planetary.
you can essentially
What
do
was that?
synthetic aperture photometry, and that ties into your flare stars. You basically just integrate over the ideal Balmer lines or blue lines and total flux measurements via that
It's a
method.
great idea. You can use the zero order.
Okay, so one of Bob's questions, I'm rushing through here because we only have 2 minutes left. And by the way, we did put in a plug for Polaris. PRNU, which is this pixel response non-uniformity map. I'm convinced that the telegraph noise is overwhelming that. For flat fields, please talk to Greg Jones. He'll be happy to disabuse you of anything you ever thought about flat fields. He wants me to elucidate on my concept of a closed framework of accountability. It applies in anything. I use it primarily with managers that work for me. And that is, I want you to be able to express yourself within the symbols that you're using. That's a mathematical concept. And I apply that by saying in spectroscopy, I want to have my raw data, my flats and so forth that went into that preparation. And I want to have the analysis script that I applied. I want to know the source code if possible and so forth of the tools that I used all the way down to the operating system. So you get tool chain management, we get the tools, we get the data. And that way, when I make a mistake, and we all make them, I can go back, I can audit it, and I can put an errata out on my paper, and I can fix my thinking for next time.
Are you familiar with Kurt Gödel?
Who?
Kurt Gödel.
Oh, good out, yeah. The
Any system
incompleteness
with the
theorem.
syntax
Yeah, okay.
sufficient
Uh-huh.
to express its semantics
Uh-huh.
is incomplete. So bounding their symbols is, not gonna guarantee anything.
It's called the Synology box. And it's also called repositories in the cloud. I can defer some of my tool chain management to the cloud. If the cloud goes away, things are so bad, I'm probably not interested in anything more than eating my neighbors at that point. Okay. I think that so a lot of what Bob's asking for, oh, wait, there's a whole list of questions here, excuse me. How many of you guys practice parallactic angle? I know one of them does. We use as a rotator, I know that.
Seriously,
use.
we're
And we're done.
yeah, we're done.